Good day everyone, we are Team 6 from A127 and today we will be presenting on the estimation of food delivery time. These are the parts that we will be covering. The COVID-19 pandemic has dramatically changed the way we live our lives. One of the most visible impacts has been a surge in the use of delivery platform services across the entire world. With millions of people stuck at home and unable to visit physical stores, online ordering and home delivery have become a lifeline for many. However, this surge in demand has also highlighted some challenges for the food delivery platforms and their riders. One of the biggest challenges is predicting delivery times accurately. Customers want to know when their order will arrive, and they expect those estimates to be as precise as possible. Inaccurate delivery time estimates can cause customer dissatisfaction, leading to customer churn. The dataset that we'll be working with is a real-world dataset from Kaggle that contains information about a delivery platform in India. It includes data from over 30,000 orders with information on the delivery time, pickup and drop-off locations, and the rider attributes such as their ratings and mode of transport. By analyzing large datasets of delivery orders and rider attributes, we can identify patterns and insights that can help improve the delivery process and ensure a better experience for everyone. This leads us to our problem definition. Can we estimate the delivery time based on the delivery rider's attributes? By following this architecture, we can ensure that our data project is well-structured, efficient, and successful. The first step in data cleaning is data retrieval from Kaggle. Once the data is retrieved, the next step is data cleansing. This step involves identifying and correcting any errors or inconsistencies in the data. The data cleaning process includes handling NaN values, correcting formatting issues, removing duplicates, and dealing with outliers. After cleaning the data, the next step is to export it in a format that is suitable for analysis. Once the data is exported, it's time to perform EDA. After loading the dataset, we need to identify the data types for each column. In this specific case, we need to convert the time taken column from an object type to an integer type. To achieve this, we can strip the string to obtain a numeric value. Additionally, we may need to cast some float columns to integer for use in seaborne charts. It also involved filling NaN values in the most categorical columns with the mode. The time taken column containing NaN values was also dropped as it is the response variable. Any rows with 0 values in lat and long columns were also dropped. When removing outliers, ratings higher than 5 was corrected to 5. The edge outliers were retained, and we take the absolute of the negative outliers in the restaurant latitude and restaurant longitude respectively, as we believe it could be from an error in data entry. We also perform some renaming and formatting operations on our columns. We use the camel casing convention to rename our columns. We also remove any unnecessary white spaces in the variable values to ensure uniformity across the entire dataset. Lastly, we export the clean data to a new CSV and push it to a repository for use in Google Colab.
Okay, I'll now be presenting on our EDA. We first start by looking at the numeric columns. We set out to understand the distribution of our response, which was the delivery time taken, and the other numeric variables. We can see that our response variable was positively skewed, meaning that there are more time taken on the lower end of the spectrum. And there are some outliers in our edge, but we'll not remove it because we believe it represents our data accurately. And ratings were generally above 4. We see the correlation, that no two variables are strongly correlated to time taken, and that ratings were negatively correlated to time taken, which makes sense as higher ratings led lower time taken. And we understand our data geographically by drawing a line across to see that there were more orders on the south of India. Here we look at our categorical columns. We look at the weather and we observe that sunny led to a lower delivery time taken. We can also see that the traffic density generally led to a higher delivery time taken if it was more packed. And the single factor that affected delivery timing the most was taking on multiple deliveries. We also see that in semi-urban areas, delivery time taken was the highest. This can be due to the lack of road infrastructures and the distances from restaurants that resulted in the greater taken. We observed the average time taken throughout a day for delivery. We see that during lunch and dinner periods, as observed here, the average time taken was generally longer. We felt that there was a lack of numeric columns, so we engineered our own using the Haversine formula to develop the distances from a restaurant to a delivery location based on the latitude and longitude of our data. We can see here that in greater distances, the traffic density tend to be much more packed and that there was more time taken. There was greater time taken. We see the correlation of distance to our time taken, it was a moderate one as well, 0.32. We then further engineered speed from our distances to further understand the delivery vehicles and speed. We can see here that motorized vehicles have a higher distribution of delivery speed going above 60 km per hour, whereas bike did not have anything beyond 50. We can also observe that vehicle condition affected the delivery speed as observed in the increasing median of the delivery speed based on the increasing vehicle condition. We can see that speed does not really have a very strong correlation with any other variables as well.
Machine learning. The first sort that we'll discuss will be models using numerical features. Then we'll move on to models that combine both categorical and numerical features. After that, we'll add in our engineered distance feature. And finally, we'll compare the result across the different models and features. From the 19 features, we had only 2 that were numerical, age and ratings. From the EDA we did, age and ratings have a decent correlation with delivery time. So we decided to start with linear regression. These are the results for the univariate linear regression models. The results were not that good, it had very high MSE. So we decided to improve further by trying out multivariate linear regression, using both age and ratings. It yielded better results, however there was still a lot of improvement to be made. Because most of our features are categorical, we needed models that can deal with categorical data as well. One model that allows this is decision tree regressor. Another plus about decision trees is that it works well with the nonlinear features we have in our dataset. These models can't work with pure categories, however, so one-hot encoding will be used to convert these categories into integer binaries that the models can work with. One-hot encoding produces a lot of new columns, which can drastically increase train time. So we used ANOVA test for feature selection. It measures how significant the difference between beams of the categories are, and we drop features whose p-values aren't significant enough. That is, features with p-values larger than 0.05. We took advantage of the feature importance method available in decision trees in order to prune the features even further. After selecting the top 8 features, these are the results for the decision tree. After that, we continued with random forest regression. The hope is that by using an ensemble of trees instead of only a single one, the resulting model will be more robust and less prone to overfitting. To further improve the accuracy, we also tuned the hyperparameters of the random forest using grid search cross-validation. It selects the best hyperparameters, which minimizes the MSE for each forest, and outputs the forest with the best hyperparameter. We realized that many of our features might not be that important, and hence are just obscuring our models. So we decided to use a model with stricter feature selection, which is lasso regression. It uses L1 regularization, which penalizes the coefficient values, shrinking them to be close to 0 or even 0. This allows us to select only the features that matters the most. This is the coefficient of the model obtained and its corresponding MSE and R-squared value. The last model that we decided to use was XGBoost. XGBoost iteratively adds decision trees to the model, where each tree corrects the errors made by the previous trees. It utilizes L1 and L2 regularization to prevent overfitting and gradient-based optimization to update the weights of the tree. We decided to use it because it works well with the complex and nonlinear nature of our features. Even without cross-validation, XGBoost outperformed all of the previous models, and further improving it using the cross-validation function available on the XGBoost library, we managed to increase its accuracy on the test set even further. These are the results of our models. We then tried to incorporate our engineered distance feature that we made during the EDA on all of the models. The result was really surprising, as with adding only one engineered feature, we managed to increase the accuracy of the models by quite a decent margin. Here we can see XGBoost jumping from an R-squared score of 0.7 to almost 0.8. This shows the importance of EDA in machine learning. Selecting the best features or even engineering new features that suit the problem domain well reduces the noise in the dataset and prevents overfitting. We learned that having a single good feature is oftentimes better than having lots of mediocre ones.
Okay, I'll now move on to the data-driven insights from our EDA and machine learning. Before we answer the main question of delivery timings, we also seek to understand if there was any biases beyond non-performance metrics that affected the deliverables ratings. We're happy to say that based on our EDA on the categorical features, we could not find any relation. Hence, we conclude that there are no biases in the ratings within this dataset. So now to answer our main problem, what are the factors that affected delivery timing? From the numeric perspective, we have positively correlated variables like distances, multiple deliveries, and age that affected delivery timings. Ratings, on the other hand, negatively correlated with our delivery timings. And our top 3 categorical features were traffic density, city terrain, and weather that affected the delivery timings. So, on to using our machine learning models to estimate delivery timings. We are confident to say that our XGBoost model was 79% accurate in estimating the delivery timings with a marginable error of just 18 in the MSE. And here are our data-driven insights and recommendations. The first is for the platform to further optimize their algorithm to minimize the delivery distances between a user and the nearest restaurant. The second is for the platform to allow users to prioritize their deliveries where they can pay a greater fee to ensure that a delivery is only delivering his or her order and not multiple other orders to reduce the delivery timing. And the last is a recommendation for all users of the platform to try and avoid peak lunch hours between 12 to 2 p.m. and avoid peak dinner periods like 5 to 8 p.m. for faster delivery timings. And with that, we end our presentation. Thank you.